Hi, I'm John McPhee at the University of Waterloo in Canada, and I'm the Canada Research Chair in Biomechatronic System Dynamics. Today, I'd like to talk to you about some of the research work being done in my group. Here's a photo from 2020 before COVID struck, when we were doing a typical Canadian sport called curling. Here's an overview of my talk. We do a lot of work on modeling and model-based control, and in this particular presentation, I'm going to focus on applications to stroke rehabilitation robots as well as exoskeletons. In general, the theme of our research is to predict and optimize the movement and the control of biomechatronic systems using dynamic models. When I say biomechatronic system, I mean really any system in which the human is interacting with a machine or a device. So it would include examples like exoskeletons, prostheses, but also rehabilitation robots, even automobiles, sports equipment. They all involve a human interacting with a machine. We create models of these systems so as we can optimize their performance. And we're really encouraged by the fact that recently the United States Food and Drug Administration has endorsed the use of computer simulation to replace some of this very tedious and time-consuming, expensive clinical trials. So in lieu of these clinical trials, computer simulations can be used to support an application for approval of a new device. There's very many challenges in creating these simulations to support device design. First of all, we have to model the device. Well, we have a relatively good handle on that, but modeling the human and their interactions with the device can be extremely challenging. Furthermore, if we don't have experimental data and we're trying to do what-if simulations to predict what will happen if a user were to use a device, then that is another research challenge. And finally, if this is a device that's being used by a human, presumably the control has to occur in real time, which is a remaining research challenge that we are tackling in our group. So here's an example of an assistive device that many of us have used. It's called electric power steering, or EPS. This was a project we did in collaboration with Toyota, where we were using an integrated model of the human and the vehicle in order to create EPS controllers that we could tune for different driver populations, be it older drivers or younger drivers. The model itself was extremely detailed. So for example, we had cognitive delays in a path following driver model. There were stretch reflexes in the system. There was a detailed musculoskeletal model of the driver who was applying a torque to a steering wheel. That torque is measured by an electric power steering system, and then an additional torque is applied to help the driver. Finally, that steering torque goes to a very high fidelity vehicle model, which follows a trajectory, which may not be the desired trajectory. And so the human again applies corrective actions and the loop continues. And using this model, we were able to develop some model predictive controllers that worked very well for different driver types. But today, I'm going to focus on modeling and model-based control with applications to rehab robots and exoskeletons. So I won't speak anything more about automobiles. Here's our methodology in one slide. First of all, we create integrated models of systems that can have components from many domains, so biological, mechanical, electrical. And to do so, we use a branch of mathematics known as linear graph theory. We then implement these graph theoretic algorithms within symbolic computing, and in our case, we use the Maple language for a couple of reasons. First of all, we're able to generate very fast simulation code, and for any work involving optimization or optimal control, you absolutely need fast simulation code. And secondly, because we have our system models and equations in symbolic form, we can easily get exact derivatives like gradients and Hessians and Lagrangians that are needed to support the optimization work. We're then in position to solve optimal control problems for what-if simulations of biomechatronic systems, and that allows us to predict what will happen before we actually run experiments. And then finally, using these models, we can create real-time controllers for the assistive or rehabilitative devices. Here is an example of a model of a person getting up from a chair, a musculoskeletal model. We've created a model of the system using the package called MapleSim, which was spin-off from our lab. MapleSim generates automatically the governing equations of motion for the system by using an internal linear graph representation of how all of the bodies and the joints and the muscles and the forces are connected. And with those equations, we can automatically generate simulations. As I mentioned before, having the equations in symbolic form allow us to create very fast simulation code. In terms of the human model, the musculoskeletal part has been tackled for the last couple of decades, and so we're starting to have a good understanding of how neural commands in the form of muscle excitations get mapped to muscle activations, which create muscle forces. And then through the geometry of the muscles crossing joints, we can obtain joint torques, which drive a multi-body skeletal model of our human. And the output is motion. Of course, we might run this loop in reverse, which is actually very common, where we measure the motions first and we work backwards to get joint torques and muscle forces. But if we're trying to do predictive what-if simulations, typically we follow the forward path. And the big fly in the ointment, if you will, is what is the human doing in all of this? So what decisions is the human making based upon what we are perceiving our motion to be and the commands we're sending to our muscles? Well, there's been a number of approaches in the literature as to how we might model the human motor control system. And the most basic method is to use some sort of a feedback and or feed forward controller. And I'll give you an example of one when I start talking about a stroke rehabilitation robot. More recently, a number of research groups are pursuing the idea that humans move so as to minimize some cost function. And if that assumption is true, then we can use optimal control theory to determine what would be the human inputs to the musculoskeletal model. What are the optimal muscle excitations or activations that create this desired movement by the human? Lastly, and very recently, there's been some work that has showed that a semi-optimal control method, nonlinear model predictive control, can also predict how human moves. And the advantage of using an MPC approach is that although it requires a cost function and therefore an assumption, it can support real-time simulations. And in terms of device control, this looks like a very good candidate, especially if it gives us a good representation of what the human motor control system is doing. I'll give you examples of all of these in the next 20 minutes. Some cost functions are easy to find. So for example, the Olympic motto is faster, higher, stronger. And it turns out that if we're trying to predict the movement of Olympic athletes or elite athletes, we simply need to use one of these cost functions. So this was a project we did with Canada's national track cycling team, in which we're trying to optimize the technique of the cyclist coming out of the gate. You can see how they throw themselves forward just as the gate releases, and there's a back and forth movement of the hip, and that's basically to maximize the torque applied to the crank. So to study this strategy and to determine what is truly optimal technique, as well as optimal configuration of the bike for a given rider, we created a detailed model of the cyclist and their bicycle. And in order to drive this predictive dynamic simulation, we didn't use any experimental results, no experimental data. We simply maximized the distance traveled in the first 4 seconds of biking. And the result from this optimal control problem looks extremely similar to the technique developed by Olympic athletes over the last years. So throw forward out of the gate and then a back and forth pumping movement in order to maximize the torque and get up to speed as quickly as possible. And then once you're up to speed, you have the momentum of the vehicle, the bicycle, to carry you over that top dead center location when it's difficult to apply a lot of torque. And so you don't have to pump your hips forward and backwards so much. The point is, we were able to find actually a slightly better technique than the Olympic athlete using a mathematical model and by solving an optimal control problem. What do we do for activities of daily living though? Somebody is walking or somebody is getting out of a chair. What is the cost function that the human is minimizing? This is a very challenging and open research question. So we've done quite a bit of work on modeling human gait. And in order to do a predictive simulation where we're not measuring ground reaction forces, we have to model them using detailed models of foot-ground contact. Turns out to get a good match to experiments, we had to play around with 6 different components comprising a cost function. And those 6 different components include terms like muscle activations, which are representative of effort, metabolic energy cost, even the jerks in the model, jerk being the derivative of acceleration. And it's known that a lot of people move so as to minimize the jerk because it creates smooth movements. So it seems that for activities of daily living, there may be many factors that need to go into the cost function that a human is minimizing. There's some evidence in the last 20 years that the CNS, which controls voluntary human movements, is comprised of 2 terms, a feed-forward term from an internal representation of what the human is doing, or an internal model, and then a feedback term in which we use sensory information to correct for errors in our movement. And if that is true, then there's a very good analogy with model-based controllers like NMPC, which use an internal model to predict a future trajectory and then feedback information to correct for those prediction errors. So it seems like an NMPC could be a very good surrogate, the human movement control system. Here's how the NMPC algorithm works. So essentially we have some states in our system that are changing in time. We have some inputs to our system that we are trying to determine, and this is our current time. We use an internal model or an internal representation to determine the optimal inputs over some finite horizon. And sometimes MPC is called receding horizon control. We then apply those optimal inputs for one time step. And then we march forward in time and we repeat the whole feedback, the whole process over again. And in that way, we get a semi-optimal solution that can run relatively quickly, which makes it not only a good candidate to represent the human motor control system, but also as a candidate for an assistive or device or rehabilitative device controller that needs to run in real time. It's been shown that NMPC captures our ability to adapt to changing tasks and environments. So this is a work from a few years ago in which a musculoskeletal model of the human arm driven by 6 different muscle groups is trying to reach to an object which is initially at A, the hand is at O, but partway through the reaching to point A, the target is shifted to a new point B. And you can see the results from experiments as well as a simulation using an MPC, where there's very good qualitative agreement between what the human does and what the NMPC predicts the human is going to do. So let me switch now to talk about applications to stroke rehab robot and exoskeletons. So it's known that strokes frequently lead to impairments of the upper arm. And if you're fortunate enough to survive a stroke, then you probably need to do a lot of rehabilitation, which typically involves many reaching movements. Well, that can be very time consuming and boring and repetitive, which is something that robots are good at. And so it seems like the rehabilitation robot that's shown here in our lab can support the work of a physiotherapist or an occupational therapist. So what we envision is, instead of one therapist working with each patient, perhaps we have one robot with each patient, providing quantitative feedback to the patient, not just qualitative. And these robot patients are being supervised and supported by a smaller number of therapists. Well, this particular robot resulted from a collaboration with the Toronto Rehab Institute and Quanser. Quanser made the physical robot, and then we augmented it with a force torque sensor at the end effector. The robot itself has 2 degrees of freedom, so it's free to, the end effector is free to move anywhere within the horizontal plane. It's driven by a couple of DC motors, 1 and 2, shown back here. And we have force measurements at the end effector, which is basically the force between the human and the device. Using MapleSim, we could generate symbolic equations and optimize code in the usual sort of structure. So TR are the robot torques. These are the torques created by that interface force. We have the usual dynamic terms, as well as joint stiffness terms, friction in the motors, as well as friction that is below the end effector as it slides over the surface. We decided to start with a relatively simple robot controller, which is a force field control. And this was presented in 2020 at CDSR. We looked at 2 types of force fields. The first was assistive, whereby the user was guided along the trajectory from the initial position to the target position. And so if they got off the desired trajectory, the force field pushed them back onto the desired trajectory. We also investigated a resistive force field where the user was actually pushed off of the desired trajectory. Now, we were unable to test on stroke patients this past year because they represent a vulnerable population, and because of COVID, we were unable to work with our local hospital, even though we have ethics clearance to do so. So until we can start testing on real patients, we used a human model from the literature. And this human model has a feedback term. It's a conventional PD feedback term, where E is the error in the trajectory that we're trying to follow. There's a feed forward term that has some memory in it, because the current feed forward term is actually a linear combination of the feedback term and the feed forward term at the previous time step. And then the total assistive force that we apply to the human hand by the robot consists of the sum of those 2 terms, feedback and feed forward. Plus, we've added a disturbance term to account for tremors and other disturbances associated with stroke patients. So we ran a therapy session in which we initially applied no field whatsoever. And so the green curves represent the subject trying to go from a starting point to a target point with no assistive or resistive field whatsoever. And these green curves are the same top and bottom. They look different because the scales are different. Then, after a couple of trials, we apply up here an assistive field that helps them do a better job of reaching to the target. And in this therapy session, we apply a resistive field, which really causes some problems in trying to reach to the target. Initially, the patient is not successful in reaching the target because of those disturbance and noise terms. And the resistive field just makes that even worse. However, when we remove the fields in the 2 therapy sessions, the patients who are receiving an assistive field do worse in reaching to the target. The patients who have been struggling against the resistive field actually do much better in reaching towards the target point. And these simulation results are actually very consistent with experimental results in the literature, which shows that resistive training can have a highly beneficial impact on recovery of motor functions following stroke. So we then went a little bit farther. We wanted to develop some controllers of the robot that took advantage of an underlying internal model. So to create this unified model of our system, well, again, we had our 2 degree of freedom robot model from before. Now we augmented it with a 3D human model with 5 degrees of freedom. And those 5 degrees of freedom are at the shoulder, elbow, and wrist joint. We've included shoulder rhythm so that the scapula rises and lowers as the shoulder raises and lowers. And there are 29 muscles wrapping over surfaces driving the musculoskeletal model. And these models are modeled using a typical hill muscle approach, in which you see here the muscle force is a function of the muscle length, but also the rate of change of length. We then created optimized simulation code using MapleSim, and then we were able to develop some model-based controllers that took advantage of this internal representation. This is a somewhat complicated slide, but on the right, you can see the nonlinear model predictive controller that we have created using the musculoskeletal model. Now, this has to run in real time. We're trying to track a desired trajectory in real time, supply torques to the robot, measure the robot angles and the interaction force, and continually update this process in real time. Now, the 3D model we created is fine for testing our controller in simulation, but it's too complex to run in real time within the controller. And so from our 3D musculoskeletal model, we've created a simplified 2D version. So we project the 3D musculoskeletal model onto the horizontal plane. We make sure that their responses to the same inputs are the same. And this gives us a smaller model that we can now run in real time within the MPC. In terms of the cost function that we're optimizing within the NMPC algorithm, we have 3 different terms, and we can weight them all differently. We could minimize the robot effort, or we could minimize the human effort, which doesn't always lead to the fastest motor recovery. Or we could minimize the tracking error from the desired path that the therapist wants the patient to follow. NMPC is very powerful in the sense that while minimizing some cost function, it can also satisfy constraints on ranges of the states, for example, ranges of the robot torque, and even ranges on the muscle activations, which should be between 0 and 1. So let's have a look at how this NMPC controller of the rehab robot performs. So in the first case, we're going to do some simulations to evaluate the robot performance, and we've used a control subject on the left and another subject on the right that absolutely is putting out no muscle force whatsoever. So if you look at the muscle activations, you see the 6 different muscle groups represented for the control subject on the left and no muscle activations on the right. As a result, the robot torques are a little bit higher for the subject on the right, who's not using their muscles at all, versus our control subject. In both cases, the interaction forces between the human and the robot are very, very low within the plane. And perpendicular to the plane, the magnitude basically represents the weight of the arm sitting on the end effector. So again, we are unable to test this on real subjects, at least during the COVID pandemic. So we tested it on a healthy subject in our lab. And the subject was instructed to relax their arm completely and try not to apply any muscle activations whatsoever. And so this was basically an attempt to reproduce these simulation results. And so what we found was that our subject was unable to completely relax all their muscles. So on the bottom row here, we can see the measured EMG from the flexor and extensor muscles. They're not zero, they are small, but they're not zero. However, when we look at the predicted motor torque versus the measured motor torque, we see very good agreement between the simulated predicted torque in the solid lines and the shaded curves that we get from experimental measurements. The tracking error is quite good. You can see the position error in tracking is less than a centimeter. Good tracking on the velocity target as well. However, when we look at the interaction forces, we get a good agreement within the plane. But in terms of that vertical force, we see that the user is in fact using their muscles. And instead of that full 30 Newton weight resting on the end effector, the user is supporting some of their load. And the force on the end effector in the vertical direction is much less. Despite that use of the muscle activations, again, we get good agreement between the predicted and the simulation results, predicted and the experimental results, and good agreement in the trajectory tracking performance. So where are we going next with this? Well, we want to tune those weights of the controller for different subjects, and to do so, we're using deep reinforcement learning. You'll see some results from us in the literature very soon on this. And of course, once we get through the pandemic, we'll be testing this on real subjects at our local stroke rehab center. So finally, let me move on to talk about exoskeletons and the work we're doing there on model-based control of exoskeletons. So one of the obvious problems that we want to tackle is the fact that users of commercial exoskeletons, like the one shown here, are told to use crutches. And that means that it seems to defeat the purpose of using an exoskeleton. And it means that your hands are no longer available for other tasks if you're being forced to use these crutches as well as the exoskeleton. We would like to just use the exoskeleton to provide active balance control, at least for just standing, let alone walking. And for this balance control during quiet standing, there's actually very few solutions been proposed in the literature. So to tackle this problem, again, we created an integrated model of the subject wearing an exo. In this case, it's the Exo H3, which is from Technate in Spain. It has motors at the hip, the knee, and the ankle, all of which we can control. To represent what the human is doing, in this particular case, we used an LQR controller, which also tries to minimize cost function. In this case, we were looking to minimize horizontal movement of the center of mass during quiet standing. And with this integrated model, we are going to develop, or we are developing, exoskeleton controllers that we will deploy on the device in order to maintain balance in the presence of noise and external perturbations. So one problem with creating models is identifying the parameters for those models. Well, for the exoskeleton, it's not too difficult. We can take it apart. We can measure the mass, center of mass, moment of inertia of all of the parts and put it back together. We can even test the various joints and the joint properties on a human dynamometer like the biodeck shown here from our lab. And if you look at some results we've obtained for torque versus speed at the different joints, you can see that we're able to come up with fairly representative damping models for the exoskeleton's passive joint properties. And these were presented last year by Keaton Inkle at Biorab. In terms of modeling the human, we've again turned to MapleSim to generate symbolic equations and derivatives, which we then use to create our controllers. So to start with, we've created a model of a human. Again, it's using this LQR controller for two subjects who are being pushed at the hip joint. And so you can see that the LQDAR does a very nice job of maintaining balance of our control subject. We have a second subject who has sustained a spinal cord injury, and we assume that their torques that they can apply are limited to only 40% of our control subject. And so our control subject uses a combined strategy at the ankle, knee, and hip in order to maintain balance. Whereas if you look at the scale for the SCI subject, you can see that they're unable to maintain balance when subjected to this push at the hip, and they fall over. We're now working on replacing that LQR model with an NMPC model, which will be presented by Mr. Inkel later this year at EMBC. So again, these are results for the control subject not wearing an exo. Now we're going to put that exoskeleton on the SCI subject who was unable to maintain balance before. And now you can see that with this controller running on the exoskeleton is able to maintain balance of the SCI subject, which was exactly our goal. Our next steps in this project is to test our algorithm on physical subjects now. This is consistent with the FDA approach where we design our devices and our controllers in simulation, and that way the amount of testing we need to do on humans will be much, much smaller. Another problem with exoskeletons is they require a great deal of high-level manual control, and so you can see this particular subject is using the Technade Exo, and I'm controlling the mode of the exoskeleton. So if we come to stairs, we need to stop. I need to switch the mode into stair climbing mode, and then we can restart again. And there's a lot of this high-level manual control currently required by exoskeletons. What we would like to do would be to automatically recognize the environment we're working in and adjust the mode accordingly. So can we automate this process? So to tackle this, we envision a user of an exoskeleton wearing some sort of a wearable camera, perhaps a chest-mounted camera like the one shown here, and to come up with algorithms that automatically identify the environment in which we're going to be using the exoskeleton. We gathered a lot of images, and we trained a deep convolutional neural network, a CNN, in order to recognize 3 different terrains at a speed of 5 frames per second. And 5 frames per second we felt was fast enough to automatically do mode selection control on the exo, because exoskeleton workers don't move very, very quickly. And the 3 different terrains we were interested in were level ground walking, going upstairs, and going downstairs. And in order to have a good convolutional neural network that accurately recognized the terrain we were dealing with, we needed a lot of images, which means we needed to do a lot of data collection, like the experiment that you're seeing here. Now, this work is led by Brock Lashofsky, who's finishing up his PhD, and he was able to obtain 95% classification accuracy, which he presented in 2019. You can see the confusion matrix above, which confirms that good accuracy of the CNN, except for a few cases. And so in the left column, these are examples of stairs that were misclassified as level ground. And on the right column, you can see that these are examples of level ground walking that were misclassified as stairs. And so you can see how an image like this one in the top right, which is actually a hallway, a level hallway, could easily be confused with a staircase. And given that, we should always make sure that there is an override switch that prevents a change in mode when none exists in real life. So there has to be an override switch that the exoskeleton user has access to. Since then, we've increased our data collection from 34,000 images to over 900,000 annotated images of RGB images, high resolution, now classified into 12 different classes, not just 3. This is available publicly on IEEE Dataport, and the idea of making this available to all researchers is that now we can compare our algorithms on a common data set, as opposed to trying to draw conclusions about different algorithms that have all been trained on different data sets. So this allows us to compare apples to apples, if you will, instead of apples to oranges. Very recently, we've trained a new CNN on this new data set, which allows for 12 different classes. So for example, we might have a transition from going downstairs to level ground. We might have steady walking on level ground, or a transition from level ground to going upstairs. These images were collected both indoors and outdoors across 3 different seasons in Waterloo, which means that we have a really wide variety of ground cover, including snow, fallen leaves, bright sunlight, overcast days. So it's a very rich data set. And we've used this data set now to train and compare 12 different popular CNNs. And if you're interested in the results of this latest work, there's a preprint available on bioRxiv. Lastly, I want to talk briefly about upper limb exoskeletons, because these have great potential for use by assembly line workers. There's a lot of shoulder injuries, especially by workers who are lifting heavy loads all day long. Now, exoskeletons have great potential to reduce workplace injuries, but it turns out that commercial versions only offer passive assistance. So in other words, they're spring-loaded mechanisms that support the arms of the user, typically as they work in some sort of awkward position, but they don't provide any active assistance. And so what we would like to investigate is how to combine the best features of both a passive exo as well as an active exo, without making the exoskeleton too heavy for practical use, of course. So again, we turn to a model in order to investigate different controller designs as well as different device designs. In this particular case, Ali Nasser, who is leading this work, has developed an integrated model of a human user and an exoskeleton made by Levitate, the airframe exoskeleton. An interesting thing about this model is the underlying structure of the human arm is different from the structure of the exoskeleton, as you can see in this animation. They both allow the same degrees of freedom of the arm to which they're both connected, but the topology along the way is different, which creates a closed kinematic chain. And a closed kinematic chain gives rise to differential algebraic equations, which are harder to solve and control compared to the usual ODE approach. We didn't run into this problem for lower limb exos because essentially the structure of the exo is the same as the human, and we can just lump the exoskeleton parts in with the human body parts, and there's no closed kinematic chains. We've used this model in order to optimize a purely passive system for 3 different tasks, and this has been presented by Ali Nasser. And now we're ready to add assistance to this exoskeleton. But how do we know what the user wants to do? How do we know that the user wants to lift something or lower something? And so one good measure for human intent are EMG signals, because EMG signals fire before the actual movement. So what we did was, from this experiment, which would involve some pick and place operations, we measured both EMG as well as human movement. And we've created another CNN, another neural network, that maps measured EMG signals to human joint angles and torques at a later instant in time. And that's how we're able to use EMG measurements in order to predict what the human wants to do. The results from these different neural networks are quite interesting. We've trained 4 different neural networks: an artificial neural network, a recurrent neural network, a convolutional neural network, and a recurrent convolutional neural network. It turns out that the recurrent networks have relatively small errors. You can see basically the accuracy reported here for the different networks, especially when we use the kinematics from previous time steps as inputs to the neural networks. What was also interesting was that the 2 CNNs, the CNN and the recurrent CNN, do better with raw EMG data versus filtered data, which means that we no longer need this time-consuming step of filtering the EMG data, because we can use the raw EMG data into our neural network, which is going to feed into our real-time controller. So this is quite an important result. And overall, even the slowest neural network, shown at the bottom here, still can compute activation torques and other human intents with less than 5% error in about 1.4 milliseconds, which is certainly fast enough for a real-time controller. This is what we envision our controller setup to look like. Here we have MuscleNet, which is using data from position sensors on the exo as well as EMG in order to predict the torque that the human is going to apply. We have our human exo model, which is predicting the combined motion of the human and the exo. And then we're going to develop an exoskeleton controller that will take as input the human torque and then augment it with some additional actuation. Very, very similar to the way that electric power steering works, similar to the way that our rehab robot works. And in fact, we're using a similar model-based control approach in order to develop these controllers. So with that, let me draw a few conclusions and I'll end my talk. Again, I remind you that we're using unified models of humans and their machines to support both predictive simulations, but also control of biomechatronic systems. A big challenge in this work is modeling the human, especially the human motor control system. For offline simulations, such as our predictive simulations of Olympic athletes, for example, or gait, human gait, we can use optimal control methods. However, for real-time simulation and real-time control, a more attractive alternative is nonlinear model predictive control, which seems to do a good job of representing the human motor control system, which would allow us to adapt our model to the machine and vice versa. And lastly, another ongoing research problem that we're tackling is how do we combine these model-based controllers with wearable sensor signals like EMG or EEG in order to come up with the optimal performance of the human and the device. So with that, I thank you for listening today, and that concludes my talk. If you're interested in learning more about our group, it's the Motion Research Group at the University of Waterloo. Feel free to check out our website or send us an email. And have a great day.